Hello everyone, we are Team 11 and this is our robot for the ML3 challenge. It is a compact 4-wheeled robot about 20 by 35 centimeters and it carries a full sensing and control stack on board. The whole design is built to do two things well: to get over obstacles that stop a normal wheeled robot and pick things up and handles them with a 2 degree of freedom arm on the front. The part we are most proud of is the wheel. These are Pat's wheels, and we 3D printed them in flexible TPU. Instead of a solid rim, each wheel is made of claw and pad segments that bend and deform against the ground. When the robot reaches a step, the wheel folds around the edge and pulls itself up. So we can climb stairs with no extra actuators, and the shape of the wheel does the work, just by driving forward. That's the core idea of the whole robot. On the electronic side, we run a low-level STM32 microcontroller that handles everything that has to happen in real time: the motor drive signals, the wheel encoders, the servos, and the current sensing. Above that, a Raspberry Pi runs ROS2 and takes care of the higher level work: the camera, the communication, and the task logic. On the front, we mounted a 2 degree of freedom servo arm. It is kept simple on purpose, but it is enough for the manipulation tasks in the challenge. Things like opening a door by its handle, turning a QR code card, and lifting a small block while carrying it. So putting it together, the robot climbs obstacles on its deformable wheels. It handles objects with the arm, it senses its surroundings with onboard cameras, and every part of it runs over ROS2. How we actually drive it, the operator interface, and where we are taking it next with the LLM is in the next discussion. So that's the robot. Now, how do we actually drive it? The operator site is just a web page. The robot carries the Raspberry Pi and ROS2 on board. The driver only needs a browser on the same Wi-Fi. There's nothing to install. You enter the robot's IP, hit connect, and you're driving. Inside the cockpit, you see the front and rear camera feeds streamed over MJPEG, and you drive with WASD. Each key press becomes a normalized steering command and goes to the robot over a WebSocket about 20 times a second. It's a React and TypeScript app with a dark mission control layout, and it's safe by design. Let go of the key, close the tab, or lose Wi-Fi, and the robot stops within 0.4 of a second. That's 3 independent failsafes all the way down to a watchdog in the firmware. Now here's the part we're really building towards. Every time a human drives, we can hit recording and lock the run. The camera video paired with the exact steering commands labeled success or failure. So just by driving the course a few times, we collect a training dataset almost for free. Those recordings train a vision to action model that watches the camera and predicts the steering. And here's the elegant part. The model plugs in as just another WebSocket client. It sends the same commands a human would, so the robot drives itself with zero changes on the robot side. The human driver simply gets swapped out for the model. And that's where we are taking it next.